Hello, everyone. Thanks for watching this lecture of the course Software Quality Engineering. So this topic is Introduction to Software Quality Assurance. So we will have 2 episodes to cover this topic. So about the reference, so you may check the Book of Ganin, 2004, the chapters from 1 to 4, Introduction to Software Quality Assurance. So you can also check other materials on Moodle for this week. So let's first have a look at one example of software bug. So this bug was introduced in 2004 and lasted for 13 years. And this bug causes more than 3,200 prisoners in a US prison to be released up to 2 years early. So this bug shows that the software defects can actually have a very important impact on our lives. In 2016, software bugs cost the worldwide economy $1.1 trillion US. So what is a software bug? Let's first do an exercise. So in this exercise, I ask the students to choose the closest concept of the term bug. So we have 3 choices. The first choice, error. Second choice is fault. Third choice is failure. As a result, 19 students participated in the vote. 10 of them chose fault, 8 of them chose error, and only 1 of them chose failure. So majority of them chose the term fault. Is that correct? Okay, so in this episode, we will cover topics about what is software quality, why is software quality important, so what are the factors of software quality, or what are the attributes of software quality. In the next episode, we will cover topics about what is software quality assurance and the elements of software quality assurance. First, software quality. Before we look at what is software quality, let's look at what is software and what is software engineering. According to IEEE, the software is a set of computer programs, procedures, and the possible associated documentation data associated with the operation of a computer system. And software engineering, first, is application of a systematic, disciplined, and a quantified approach to the development, operation, and maintenance of software. So that is the application of engineering discipline into software. Okay. A second part of software engineering is the study of approaches of the software development, operation, and maintenance process. Okay, let's back to our exercises. What is a failure, what is a fault, and what is an error? Failure is an observable incorrect behavior of a program. It's related to the behavior of the program rather than its code. It's a behavior. A fault is a necessary but not sufficient condition for the occurrence of a failure. It's related to the code. A fault is also a bug. An error is a mistake usually made by people. It's a cause of a fault. So looking at this figure, developers or people make errors. An error can lead to a fault in the source code. And a fault may lead to a failure when the source code or the software system is executed. So there's a relationship between error, fault, and failure. Let's look at a simple and concrete example. So here, this is a C or Java program. It's a method. So in this program, we see the method name is double, which means so this method will return the doubled value of the input value. But if you look at this example, you see there's a problem. So what is the problem? If you look at line 3, so we want to return a double value of the input value. So we should have a plus here instead of star here. So what's the failure here? If we give an input 3 to this method, we will return 9. That's a failure. That's an observable, unexpected behavior. So what is the fault? So on line 3, there should be a plus instead of a star. So this is fault is associated with the source code. So what is an error here? An error is made by people, is a typo. The people made a typo, made the error, which lead to the fault in the source code. And then this fault may lead to a failure when the source code is executed. Okay. This is a simple example. In practice, there are usually 9 causes of software errors. The first one is a faulty requirement definition. So which may be a missed requirement during requirement elicitation. The second is a client developer communication failures. Client may say something, but developers may hear something else. The third category is deliberate deviations from software requirements. So there are many reasons for the deliberate deviations. For example, the project manager may decide to work on a reuse of a software library, but this library may not be exactly the same as a requirement. But in order to save time, the project manager may decide to use the library, even though there's a deviation from the requirement. Sometimes maybe there's a time pressure. Sometimes there may be a budgetary pressure. The fourth category is logical design errors. So this can be some defect in the design of the algorithm. Maybe use the actions in a wrong order, or like miss to check some input values. The fifth category is coding errors. For example, using a different API or using one API incorrectly, or make a typo. So the sixth category is non-compliance with documentation and coding instructions. Usually in a company or in an institution, so there will be some programming guidelines or policy. So usually the developers need to follow these guidelines in order for this code to be consistent. Sometimes some developers may not conform to these guidelines, so which may result in inconsistent code style. Especially when these developers leave the company, it's very difficult for other developers to understand their code and to inspect the code, to reuse their code. So the seventh cause is shortcomings of testing resources. Insufficient testing may lead to bugs in the production. The eighth category is procedural errors. Misleading user interface may lead to the user confusion and mistakes. Number 9 is documentation errors. If the documentation is different from what is actually in the source code, that is incorrect documentation. So these are the 9 causes of software errors. So what is the distribution of software errors, or what's the distribution of software defects? If we look at the figure on the left, we see 56% of the software defects are related to the issues in the requirements. And 27% of software defects are related to software design. 6% of them are related to coding. So the majority of defects are introduced in the early phases in requirement engineering in software design. If you look at the figure on the right side, so this one shows the distribution of effort to fix defects. Over 80% of the effort is used to fix the defects related to requirements, and over 13% of the effort is used for fixing the defects in the design phase. So we look at that. Requirements are the top reason for the project success or failure, followed by design. And coding only accounts for 1% of the effort to fix defects. Therefore, so we need to apply software quality assurance in the early phases of software development lifecycle. Next, let's look at the cost of the software defects found in different phases. We use software defects found in the requirement phase as a baseline. So here we assign cost ratio of 1 to the software defects detected in the requirement phase. Then for design, if a software defect is detected in the design phase, the cost ratio is 3 to 6. If a software issue is detected in coding phase, the cost ratio is 10. The cost ratio is even higher during testing and production phases. So we can see that in early stages of software development, the cost of detecting and fixing one issue is smaller. But if you find a software issue later in the software development lifecycle, the cost is much higher. So we need to be able to find the software defects as early as possible. So what is software quality? According to IEEE, so software quality is a degree to which a system, component, or process meets specified requirements. That's the first dimension. The second dimension of software quality is a degree to which a system, component, or process meets customer or user needs or expectations. So sometimes, even though your software meets the expectations, meets the specifications in the requirements, it may not meet the expectation of the users because the requirements may not reflect the user needs accurately. According to Pressman, software quality is about the conformance to explicitly stated functional and performance requirements, explicitly documented development standards, and implicit characteristics that are expected of all professional development software. So these are definitions of software quality. So remember that software quality is about whether the software meets the user requirements. So whether the software meets the specified requirements and whether software meets user expectations, 2 dimensions. Okay, so why software quality is important? Because if software doesn't have high quality, it may have a very serious impact in our daily lives. For example, software is a major component of many computing systems, including computers, mobile phones, IoTs, and many other things like the library management system, or maybe a control system of airplane. So it's a software system account for over 80% of the cost of computing systems. So these compute systems are pervasive in our daily lives. So they cover the domains of communication, health monitoring, transportation, economic exchange, and entertainment. So software defects may be extremely costly in terms of money, reputation, and loss of life. Let's look at a concrete example. A Zoom 30 is a video player by Microsoft. On the last day of 2008, the players stopped working. It's because 2008 is a leap year, and the last day of a leap year was not well handled and was not tested. So the software cannot work on that day. So what is a fix? Official fix by Microsoft is to wait until January 1st, 2009, because that's a normal day, not the last day of a leap year. So this is an example of how software quality, how our software issues may impact our daily lives. Sometimes because of a software issue, we cannot use one software. We need to wait. And there are some more severe problems or disasters related to software issues. For example, in 1988, a US battleship, USS Vincennes, mistakenly shot down an Airbus passenger plane 320 and caused the deaths of hundreds of people. It is because a software issue. And in 1991, there was a Patriot missile failure, also caused by a software issue. In 1992, a software issue in a computer-aided dispatch system in London was blamed for the death of 30 to 45 deaths. And in Canada, the Therax 25 system, which is a radiation therapy and X-ray machine, killed several patients between 1985 and 1987, because of unanticipated non-standard user inputs, which were not tested in the software. So these are some examples of the bad consequences of software failures. This is another example about a crash of a launching of a rocket, Ariane 5. So I won't go to details, but it's also caused by a software issue. It's an uncaught exception. There's another example, which is called the Heartbleed bug. It was a serious vulnerability in the popular OpenSSL software library. This library is widely used by many web servers like Apache web server and the Nginx web server. And on average, so these web servers account for over 66% of the market share. So the failure in this library causes the failure of the software bug impact the normal working of over 66% of the web servers. And also, so this failure causes the exposure of the private information of 4.5 million patients in the US. So the loss of this personal information is caused by someone exploiting the Heartbleed bug. This bug was introduced in 2012, but only fixed in 2014. So it's a very famous bug and it causes very bad consequences to the economy and also to the privacy of people. So these are some examples of software failures. There are many more. So software problems everywhere. Software problems is a pervasive problem. For example, software is commonly delivered late, over budget, and of unsatisfactory quality. Software validation and verification are rarely systematic, and they are usually not based on sound, well-defined techniques. So we will cover the definition of software validation and the verification later. Yeah. Also, software development process are commonly unstable and uncontrolled. So finally, software quality is poorly measured, monitored, and controlled. In 2002, the National Institute of Standards and Technology of the United States reports that bugs cost the US economy $59.5 billion each year. And if we can detect such issues early, so we could save over 22 billion US dollars. In 2016, it was reported that software bugs cost the worldwide economy 1.1 trillion US dollars. So software quality is a pervasive problem. So why software quality is hard to ensure? It's hard to make sure that software has a high quality. That is because software has some uniqueness compared to other products like cars, like houses, like doors. First characteristic is high complexity. So a large-scale software systems can easily have over hundreds of millions of lines of code. It's very complex. And also, the second characteristic is invisibility. For other products, you can see their shape, you can see the components. But for software is invisible. For example, you can see a door of a car, but you cannot see one component of a software system. You cannot see which part of the Facebook system dealing with user information handling, right? The third characteristic is about the limited opportunities to detect defects compared to other industries. For other industries, there are many opportunities to detect defects. For example, for doors of the cars, because it's visible, so you can detect such defects during the development stage, during the production planning stage. Also, you can detect them during the manufacturing stage, right? But for software, because you cannot see the details, you cannot watch the details. So mainly you can detect such issues during the development phase. You cannot detect them during the manufacturing, during production planning stage, because during the manufacturing, for example, it's just a copy and paste. This is about the uniqueness of a software product. Another challenge is about the environment in which software is developed. A complex and evolving environment. The software development is usually contracted, and also is subject to customer and supplier relationship. It requires teamwork, and also you need to have interfaces with other software systems. So also there may be continuous team changes. So software development to deal with the leaves of team members, but still carry on this project. Also, after the software product is released, is provided to a customer, the software developers or the software development organization need to continue maintenance over multiple years for the system. For example, Microsoft need to maintain their Windows system after the Windows system has been released to the customers for multiple years. So this is a complex, dynamic environment in which the software is developed. So it would add to the challenge for ensuring software quality. So how we can measure, how we can evaluate the software quality? So there are some software quality factors or software quality attributes that we can rely on to evaluate the quality of software systems. So there's a classical model, which is called the Mike Coss model, is proposed by Mike Hall. He proposed software quality factors, which can be divided into 3 dimensions. The first dimension is a product operation dimension, so which is about the extent to which the software fulfills its specifications, or extent to which the software fulfills its requirements. The second dimension is about product revision. It is the ability of the software to adapt to the changes. It's the ability of the software to be changed. The third dimension is product transition. It's about adaptability of the software to a new environment. For example, to adapt to the new Java libraries, to adapt to new computer hardwares, adapt to phones from the laptops. Okay, let's look at each dimension specific in detail. Okay, the first dimension is a product operation. So there are several specific factors. First one is correctness. It's about the accuracy and completeness of the required output. It's also about up-to-dateness and the availability of the information. The second one is the reliability. The reliability is about the extent to which the system doesn't fail, or is measured by the maximum allowed failure rate. Efficiency is about the system resource usage, such as CPU usage, disk usage, memory usage, and the network usage. So we want to ensure that the software use minimum hardware, use minimum resources, but still providing the specified, the needed software performance. The next one is integrity. Integrity is about security. It's about how secure the software is and how the software control the access rights of its users. The next one is usability. It's about how easy the software can be used by customers. It's about how much training is needed and how easy it is used to learn and perform required tasks. The second dimension of the quality factors is about product revision. Several specific factors. First one, maintainability. Maintainability is about how easy the software is to be changed. How easy is it to fix bugs and detect bugs. Second factor is flexibility. It's about the ability of the software system to make changes. These changes are based on the user requirements, new user requirements, or like new environment, new tasks. Next one is testability. It's about how the software support testing. For example, whether the software provides enough log files, log information, whether the software provides automatic diagnostics, like how much the software can be traced, how easy software can be traced. So this is about testability. The next dimension of quality factors is product transition. It's about the adaptability of the software to new environments. Several specific factors. The first one is about portability. It is the ability of the software to be transformed from one environment to another. Reusability. It's about the ease of using existing software components in different contexts. It is about how easy it is for the software to be reused by other software systems, or how easy is the software to reuse other software components. The third factor of this dimension is interoperability. It's about the ability of the software to interface with other components or systems. So there are many other factors such as robustness, performance, user-friendliness, verifiability, repairability, evolvability, understandability, and others. So this factor may be covered by other models that describe the software quality factors. Okay, so that's it about software quality. Today we covered what is software quality and why software quality is important, and what other factors that are used to evaluate software quality. In the next episode, so we will talk about what is software quality assurance. Thank you.